meters per second times time. All right, this is velocity, this is time. Time is just seconds. All right. When they cancel, you're just left with distance, which is meters. So like 5 meters per second, how many meters is traveled in 5 seconds, right? You'll get 25 meters. Like they cancel as necessary so that you're left with, you know, the right units. That's all that is asking. Next. All right. So we have this one's pretty easy. We have signals traveling at 90% of the speed of light. How many feet can the signal travel in 10 nanoseconds? So first we need to know the speed of light. All right, so the speed of light is 299. No, it's 299 million. 792,458. That's the speed of light. So it's traveling at 90% of the speed of light. So times, what's 90% of the speed of light? That's times 0.9. And then how many feet can the signal travel in 10 nanoseconds? So nano is 10 times to the negative 9 times 10. Okay. So how many feet can the signal travel in 10 nanoseconds? All right, so first we'll get this value here. Now multiply it by 10 nanoseconds to see how many meters it's traveling per nanosecond. And then we're going to multiply it by the conversion to feet. Right? So when we do that, pull out your calculator. 299,792,458 times 0.9 times 10 times 10 raised to the negative ninth. No. Negative. Okay. Then meters to feet. Something's not right. There we go. My units weren't multiplying correctly. All right. 2.69. and we get that number, right? So first you take this here, then multiply it by this. You're left with meters after multiplying, because this is in meters per second times meters. You're left with meters. Then you times that by feet per meter. These cancel and you're left with feet, which you should get 8.86. Like I said, yeah. This is in meters per second. This is in meters. Or no, this is in seconds. Right down here, this is in seconds. When you multiply them, you get meters. Multiply that by feet per meter. You just cancel your left with feet. And you should get 8.86 feet. It's traveled in 10 nanoseconds. That should be the answer. Well, it is the answer. Alright. According to the passive sign convention, the power associated with a circuit element is positive when Alright, so for this question, right, it's asking, according to the passive sign convention, the power associated with the circuit element is positive when it's positive when the element is absorbing power. For example, why is it not connected? 1 second. You'll be given the voltage and the current, right? Connect. Okay. You'll be given this equation. I, voltage and the current. Either or can be negative. And these, depending on how the voltage from plus to minus, if the current goes with it, this out here can be positive. But if the current goes against, it can be negative. Right? It'll make a negative out front. God. Anyways. Yeah. Lord. Anyways, if that result is positive, you have a circuit that is absorbing power. The element is absorbing it. And if it is negative, it is supplying power to something. Okay. That's that, for the most part. Alright, so this one, okay, that's straightforward. Which formula? So power is equal to voltage times the current. So you see this one right here. They just divided the V over to the other side to try to trick you. If you multiply V on both sides, you get P is equal to V times I, which is the original formula. 5. Which current is integrated over time? The resultant has units of charge, right? It's equal to P. P is a function of time. Let's go over that. This is what it means. No, erase. There we go. P as a function of time is equal to dq dt, right? Multiply that over, integrate. You have, you'll have dt, p over t is equal to dq. When you integrate both sides, you have q is equal to p, the integral of p, the function of t, dt. And which means when current is integrated, as you integrate it, you get charge, which is q. Charge is equal to q. Ah, you son of a bitch! really comfy. Huh? Oh, really? Is it windy for little Biden? Ooh. All right. So here we have I as a function of time. Is that equal to 4 minus t squared? We're given an interval from 0 t to 2 seconds. And we need to know the maximum value of the current, which is I. So what is the maximum? Go from 0 to 2. As you increase t, you'll notice that you get a negative value, so it's going down. So we need to go down in time. So when it's 0, you'll get 4 minus 0, which is 12. And from 2, the upper limit, you'll get 4 minus 2, which is 2. 2 times 3 is 6. So 0 will be the maximum, and you get 12 amps for that. Okay. Alright, we back in this. It's gone for a little while. Alright. Yeah, okay. So here's a good problem. So the question states, for the current described in the video, find the total charge accumulated at the left terminal as t approaches infinity. So, lucky for us, we have a relation, right? Let's switch here for a minute. We are going to go back here. All right, so I as a function of time is equal to dq, the rate of change of charge over time. Right. So we can multiply dt over to the other side, right? The integral of I t, and if we integrate dq, we're left with charge, which is q, from, well, the base 0 and to infinity as our bounds, because we're doing it as t approaches infinity, right? And our function I of t has a value, which is, let's see, let's go to the video, 0.25 x e to the negative 2,000 x, right? Alright, so that is our base, right here. This is our base, this is our function I, right, current. Which is 0.25 x e to the negative 2,000 x integral from 0 to infinity is equal to the charge, right? That's what our charge, whatever our charge is going to be as t approaches infinity. Alright, so how do we solve this? First, we need to integrate, alright? We can substitute, how they do in the problem is they substitute certain values, like negative 2,000. We can substitute that for a, right, and integrate it, and then plug it back in, and we can pull 0.25 out, because that's a constant. So we'll rewrite it as x e to the a of x And let's integrate that. We'll say dx, right? We'll make it like this, and we'll dummy term. So we'll do integration of parts. Let u equal x, right? And dv is equal to ea of x. All right, and v, when you integrate, what is that going to be? It's going to be e to the ax divided by a, and then du dx. Now substitute x times e to the ax divided by a minus the integral of eax a dx. Now we can pull that 1 over a. And what is e to the ax? What's the derivative of that? Well, we'll just have e ax divided by a times 1 over a. And we get, let's go up here. We'll get e to the ax a squared minus x e to the ax over a. And what can we do here? Well, we see some common factors. E to the ax. We can pull that out, right? Let's go up here. We're traveling a little messy, but that's fine. We can pull that out. E to the ax. Right, let's factor that out. And we have x over a minus 1 over a squared. Well, we can simplify this further. We don't really like I don't like fractions. So what we can do is factor out a squared. So when you multiply this whole entire expression by a squared, we get a squared, 1 over a squared times a squared is just 1. And we're left with a here. And this is a simplified answer. Right? And let's make sure that that's right. Let's go to the video. No. Or factoring out is 1 over a squared. That was stupid. The way I did it. I don't know why I did it like that. Right. So you have x over a minus 1 over a squared. Factor out 1 over a squared. Left with 1, right? But this leaves you with ax. Because 1 over a, when you factor out a squared, you're pulling out, you pull out the 1a, but, you multiply the 1 up top. See what I mean? It's like this. A over a squared, that's the same thing, right? You pull that out, and you're left with a on top. If you were to rewrite it as a over a squared x minus 1 over a squared, right? That's the same thing as it was before, and you can pull that out, right? And you're left with ax minus 1, and this is your final, integrated, simplified version up top. Right, and you can substitute a, which is negative 2,000, in the expression. Right, you plug that back in. So, let's go down here. Don't tell me you can just... Okay. Alright, so now that we have our expression, let's pull it down here. Nope, not what I want to do. This one. E to the negative 2,000 x divided by negative 2,000 squared of 2,000 x minus 1 from infinity to 0. You just plug in infinity for the first, we'll do the first one. So as negative 2,000 approaches infinity. Actually, here, since that's negative 2,000, and if you plug in infinity into x, as e to the negative infinity, this will approach 0. And that'll make this whole thing 0. Minus, well, negative 2,000 times 0 is 0. So e to the 0 is 1 over negative 2,000 squared. And negative 2,000 times 0 is 0. So that's just going to be negative 1 times negative 1. And whatever this answer is equal to Q. Okay, that's how you do 7. Which should be, right, 62.5 Q is in coulombs, nanocoulombs. Bigger C. What was the next question? Alright. Okay. So for this one was a little tougher for me. I was able to get it pretty good. Okay. So for the voltage and current described in the video, find the time at which half of the total energy has been supplied to the circuit element. Okay. So first we need to find some certain values. So if we go to the end here of this video, okay. So first, our function that we need to know is power, right? Power is equal to all right. So let's go back to here. Power is equal to dW over dt, right? Integrate both sides. You have the integral of P d, we'll put dx because we like dx better, is equal to W, which is, W in this case is energy. It's from negative infinity to infinity, but the lower limit is always going to be 0 to whatever value is infinity, which is in theory t. Oops. T, right? Time. Because it's dt with respect to time. Alright, so what we need to do now, first, you can find that if you set your limits, which were given initially, voltage and current, and power is equal to voltage times current, which is going to be our P, power, in this scenario. So we're given voltage and current, right? And to calculate the total energy supplied for part B in this question, we as something is supplying energy to an element, right? It will eventually run out of energy, and then the element itself will be fully charged. So if you approach infinity, eventually it will be fully supplied, right? Because it's asking, what does total energy mean supplied to the element, right? It's the 1.2 millijoules. That's being totally supplied to the element as it approaches infinity, if you set the bounds towards that. So what we want to know in the question is, what is the time when the energy supplied is half this amount? Well, 1.2 millijoules, right? This is when it's full. Well, Well, first let's write the, what is it? What are my numbers for what is pi equal to? We'll just do what it is integrated, so I don't have to do that now. So 0.6 divided by negative 500 e raised to the negative 500 x. Okay. So let's go back here. So p. So okay. So this is how we're gonna set it up. From 0 to time t, right? We're trying to find t. We know p, right? The e, no, 0.6 e to the negative 500 x. This is the integrated one. All right, this is already integrated. Is equal to, right? So full is 1.2. Half is 0.6 millijoules. We set it equal to half. And then we plug in our variables. 0.6 e to the negative 500 t divided by negative 500. This function minus, well, 0.6 e to the negative 500 at 0 divided by negative 500. Well, e to the 0 is negative 500 times 0 is 0. E to the 0 is 1. So we're just left with 0.6 divided by negative 500 minus 0.6 e to the negative 500 t. Oops, that 5 looks nasty. Divided by negative 500, right, is equal to 0.6 millijoules. All right, so we can see we could factor out 0.6 negative 500. So then we're left with e to the minus 500 t minus 1 divide 0.6. We can convert so we don't mess up from milli to joules, which is going to be 0.006. No. 0.6. Right. Let me make sure. Yeah. Yep. Good news, good news, good news is all they want to hear. I love Mac Miller. He's pretty good. Ooh. Made a way the scrolls roll. Anyway. Okay. So we'll divide that to the other side. Keep change flip. Negative 500. Negative 500 divided by 0.6 times 0.0006. Get that? Right. Set it equal to. Yeah. Negative 0.5. And we're left with e negative 500 t minus 1 plus 1 onto the other side. E to the negative 500 t is equal to 0.5. Grab the natural log of both sides, right? Natural log 0.5. All right. Negative 500 t is equal to whatever this number I got divided by negative 500. And we'll say natural log of 0.5 divided by negative 500 is equal to t. Our number we get is 0.0013 8, 6. And what is the question asked? Do we round? Round to what? 3 significant figures. All right, so if we convert it to milli, let's go back to these. Convert to milli. 1, 2, 3. 1.38 milli. No. Seconds. Milli. Seconds. And then 3 significant figures. 1, 2, 3. It's 1.39, 1.39, which is very close to our answer. Right. Very close. They rounded a lot more than I did. .4 works. There's like a % error with this. That'll make it fine. Alright, that's that. Next one. This one's pretty easy. For the circuit analyzed in the video, together with the tabulated voltage, find the elements that are supplying power to the circuit. So A and C, right? A and C are the ones supplying. Why? Well, let's go to the video. So after calculating, right, A and C are positive. I know, when you solve them, they're negative. And if you get a negative result after solving, they are supplying to the circuit, which is A and C. EBD are positive. They're absorbing. B, D, and E are absorbing, right? Because they're positive. Because you have P is equal to V times I. The voltage in I are already given to you. You need to determine the sign of each element. If the current is going from positive to negative, you get a positive sign on the outside of the V and the I. And if it goes against, it's negative. So you see for A, if you go to A, wherever that is, up here, you can't see it. Let's go to C. C is positive. You get a positive sign convention. This current here is going down, which is going with the plus and the minus, but there's a negative here from I, which makes it negative, right? So that's how you do that problem. If after you solve it, it's a negative result, it's the one supplying, which is A and C. Yeah, that's that. That's all the questions. So, whoop whoop. Yep.